Section 2.3 is about function composition. Function composition is denoted by that little circle. This particular one is called f of g of x, and it's equivalent to taking this second function, g of x, and putting it in place of the x in f. Okay, likewise, this function is called g of f of x, and it's the equivalent of, again, taking the second function and putting it in place of the x with g. So for an example, let's let f of x equal 2x plus 1 and g of x equal x minus 5, and I want to figure out f of g of x. Well, what I'm going to do is take f of x, and wherever I see that x, I'm going to plug in the entirety of g. And then I'll just continue on and put down the rest of f. And then I'll just simplify like I normally would. I'll distribute that 2 over the x and the 5, and then I'll combine like terms. So in this particular case, f of g of x is 2x minus 9. The first type of problems you're going to get are figuring out numeric values. So in this particular case, let f of x equal 5x minus 1 and g of x equal x squared minus 2. So if I'm trying to evaluate f of g at negative 1, remember that's the same as f of g at negative 1. Again, this second function is just replace the x and the f. And now I can just figure out what g at negative 1 is. And when I figure that out, g is negative 1. So f of g at negative 1 is the same as f of negative 1. I'm just replacing the x and f with the negative 1 I got here. And then just plug in. So f of g at negative 1 is negative 6. Now let's try the same thing with g of f at 2. So that is the same as g of f at 2. So now I just have to figure out what f at 2 is. So somewhere off to the side, I figure out f at 2. And I get f at 2 is 9. So I'm just going to replace this f at 2 with this 9. And now I just plug that 9 into x for g. So g of f at 2 is 79. Now, once you've got the hang of finding numeric values, you're going to find algebraic values, just like you did with the algebra of functions. So let's start with f of g of x. And remember, that's the same as f of g of x. So what we're going to do is we're going to start with the f, and everywhere I see an x, I'm going to plug in all of g. And then I just simplify. So I distribute the 2. And simplify. So f of g of x is 10x minus 12. Now, just like the algebra of functions, whenever you're solving these generally, you also have to find the domain. So what's happening in this equation is the g is operating first. And if we look at our g, it's sending values somewhere. And then the f comes along and takes those values and sends them somewhere else. Now G is a line, so you can input any real number into there. So the domain of G is all reals, and the range of G is also all reals. And now looking at F, it's also a line. So it also has a domain of all reals and a range of all reals. But we really don't care about that. What we're looking at is this middle step right here. If G does not send any numbers to a point that's going to cause a problem for F, so in other words, if there's no problem here, look to your first domain for the domain of the composition function. So in this case, there's no problem in the middle, so we're going to look back to this original domain for the domain of the composition function. So the domain is negative infinity to infinity. Let's try a slightly different one. We'll go the other way now. Let's try g of f of x, which again, remember, is the same as g of f of x. In this case, I'm taking g and I'm replacing the x with f. And then I'm simplifying. So g of f of x is 10x plus 3. Now, to find the domain of this one, again, remember the f operates first. So f of x is taking numbers and putting them somewhere. And again, since it's a line, it's taking them from negative infinity and putting them in negative infinity to infinity. And then g of x comes along and pulls numbers out of here. But g of x is also a linear equation, so it's not going to have any problem with any number in here. And since there's no problem here, that's going to be my domain. Okay, now let's show you one where this gets a little bit more interesting. Okay, now let's let f of x equal x squared and g of x equal radical x. And this time I'm looking for f of g of x, which is the same as f of g of x. So what I'm going to do is I'm going to take f, and wherever I see an x, I'm going to plug in all of g. And hopefully you remember that squares cancel square roots. So f of g of x is just x. Now for the domain of this, we're starting with g, and g is a radical. We have a restricted domain on this of 0 to infinity. And we also have a restricted range. It's mapping things, again, from 0 to infinity. So g takes numbers in this domain and maps them to this range. And then f comes along and takes numbers out of here. Well, f is a parabola. It's not going to have any trouble with any of these numbers because I can put any real number in here. So again, here there is no problem. So I look at the original domain for my domain of my compound function, and my domain is going to be 0 to infinity. Let's work this the other way now. Okay, so I have the same f of x and the same g of x, only this time I'm reversing it. I'm doing g of f of x, or g of f of x, whichever way you prefer to think of it. So this time I'm taking g, and everywhere I see an x, I plug in f. And again, the square and the radical cancel each other out, and I get an x. This time, though, I'm starting with the function f, which is a parabola with a vertex at 0, 1. So f starts with a domain of negative infinity to infinity and maps that to a range of 0 to infinity. And then g of x comes along and pulls numbers out of here. Well, every number in here is within the domain of g of x, so again, we have no problem here, which means that's going to be our domain. And now let's do one which is about as hard as you're going to ever see on the exams. Same basic idea. We have f of x equals radical x minus 1, and g of x equals x squared plus 2. And first I want to look at f of g of x, or f of g of x. So I'm going to start with f, and anywhere I see an x, I'm going to plug in g. So I start with my f, and because this one's a little more complicated, I'm going to put parentheses around the g of x when I add it in. And then I'm just going to simplify. So g of x equals x squared plus 1. And now I have to find the domain of this. Well, we start with g of x. So g of x is a parabola with the vertex at 0, 2. So it has a domain of all real numbers, or negative infinity to infinity, and it maps them to the range of 2 infinity. Then f of x comes along, and it has a restricted domain of 1 to infinity, but no number in here is outside this domain, so there aren't going to be any problems in here. So again, there's no problems here, so there is my domain. Negative infinity to infinity. Let's try this one more time. And we're going to use the same two functions, except we're going to compose them the opposite way. So we're looking for g of f of x, or if you prefer, thinking of it like this. So this time I'm going to start with g, and everywhere I see an x, I'm going to plug in all of f. And remember, squares cancel square roots, and I just simplify. So I get a solution of x plus 1. And now I just need my domain. This time I'm starting with f, and that has a restricted domain of 1 to infinity, and it maps that to 0 to infinity. And then g of x comes along, and it can take any number, so no number in here is going to cause a problem for g of x. So again, no problems here. Look here for your domain. The last thing we're going to do in this section is function decomposition. So in this case, we're given a function h of x, in this case the cube root of x squared minus 1, and you'll be told you want to find f of x and g of x such that f composed with g of x is h of x. And the first type of problem you're going to run into is you're going to be given the g of x, or this second function. Whenever that's the case, what you're going to do is go back to your original function, circle whatever g of x is, and replace it with x. The f of x is this new function. It's just that simple. The second type of problem you'll have is where you have to find the g of x on your own. So exactly the same type of problem. I've made this one a little bit harder by having both a numerator and denominator. But same question. I'm looking for f of x and g of x such that when we compose them together they make h of x. So what we're going to do is we're going to pick something to circle. And the rule is whatever I circle has to include all the x's, and it has to be the same. And I can't cross the division line, but I can circle things more than once as long as they're the same. In this case, I've circled x cubed. Whatever I've circled is my second function. And then I do exactly like I've done before. Whatever I've circled, I replace by x. And this new function is my first function, or in this case, f of x. And it does not get any harder than that.